Ascending limb is only permeable to solute. In thin ascending limb, sodium and chloride absorbed passively into interstitial space, while in thick ascending limb there is a cotransporter on the cell membrane. It allows absorption of sodium, potassium, and chloride ions from filtrate into cell. From inside the cells, these ions are transported into interstitial space through channels present at the basolateral membrane. Some of the potassium that enter the cell leak into lumen, making it positive. Other positive ions like calcium and magnesium present in filtrate will repel from positive charge inside lumen and move through paracellular spaces into this interstitial space. All these ions make this space hypertonic. On the other hand, descending limb is only permeable to water because it contains aquaporins. As you know, water loves to follow salt content. Water will come to this interstitial space through aquaporin. So, as we go up an ascending limb, solutes are absorbed into interstitial space. The filtrate here becomes hypotonic and less concentrated. That's why osmolality of filtrate is less as it reaches distal tubule in cortex region, and as we go down in descending limb, water is absorbed into this space. Filtrate here becomes hypertonic and more concentrated. This is called counter-current multiplier mechanism of loop of Henle that create medullary osmotic gradient, meaning this mechanism increases solute concentration within the renal medulla interstitial space. Urea and water absorbed from collecting duct is also coming to this space. In interstitial space, blood is carried through vasa recta. Blood flows through vasa recta very slowly. It allows enough time for passive diffusion of water and solutes. Vasa recta also has limbs. Its descending limb is close to ascending limb of loop of Henle, and ascending limb is close to descending limb of loop of Henle. As blood goes down into medulla region, it is entering in very hypertonic environment. It picks up salt and drops water. As water leaves the blood becomes concentrated. While as this concentrated blood goes up through ascending limb of vasa recta toward low concentration environment, it picks back water by osmosis that was coming from descending limb of Henle toward the salty interstitial space and drops back salt into this space. Water that left the blood on the way down is largely reabsorbed on the way up. As salt that enters the vasa recta is equal to salt that leaves the vasa recta, net salt removal from medulla region is zero that preserve this interstitial hypertonicity and medullary osmotic gradient. This means the blood leaves the medulla at roughly the same salt concentration it entered, that is 300 milliosmoles. So if the net salt removal from the space is almost zero, then does this mean no absorption happened? No, absolutely not. Now, keep in mind that vasa recta must absorb some salt to take reabsorbed water from tubules. If they did not absorb any salt, they would not be able to take reabsorbed water and nutrients and return it to the circulation. Then, how does it preserve the medullary gradient? You forget, secretion also happened. Yeah, that's how it preserve it because solute absorption in the descending limb is balanced by solute secretion in the ascending limb, resulting in no net solute removal, while allowing net water reabsorption. This is called countercurrent exchange of vasa recta. But there is another important thing that the blood that returned back to the cortex has slightly high osmolality, which is around 350 milliosmoles as compared to blood that was entered into medulla, which has osmolality of 300 milliosmoles. There are two reasons for this. First is solute is not 100% returned back to interstitial space from ascending vasa recta. So that tiny fraction of solute that retained in blood raises its osmolality. Second reason, solute is continually absorbed from tubules to this space that is replacing that lost solute. Although countercurrent exchange prevents net solute washout from the medulla, very small amounts of solute reabsorbed from tubular fluid and incomplete equilibration cause blood leaving the vasa recta to be slightly hyperosmotic compared with blood entering it.